Hello students, welcome to lecture 14. In this lecture we will discuss properties of maximum likelihood estimators. Recall that theta hat MLE, maximum likelihood estimator, is an estimator such that density function we are considering as a function of theta hat MLE is greater than equal to the density function as a function of any other theta. So, this is the basic definition, and if the likelihood function is differentiable with respect to theta, then theta hat MLE is given by this expression del f del theta at theta hat MLE is equal to 0. Equivalently, we can write in terms of the log likelihood function del L del theta at point theta hat MLE is equal to 0. These MLE conditions can be extended to multi-parameter cases. We will now discuss some important properties of MLE. MLEs are backed by elegant mathematical theories. They possess desirable properties of good estimators, particularly for large samples. In many situations, MLE turns out to be an MVUE, minimum variance unbiased estimator. For some distributions, closed form solutions of likelihood equations may not exist. In such cases, MLEs may be constructed numerically through iterative algorithms, and their properties may be studied. For example, we may determine the bias, variance, etc. Some properties of MLEs are described next. The first property is an MLE, maximum likelihood estimator, may be biased or unbiased. In the example of IIT Gaussian samples, we established that the MLE for mu, that is mu hat MLE, is equal to summation xi going from 1 to n divided by n, and similarly MLE for sigma square, sigma hat square MLE, that is equal to 1 by n summation I going from 1 to n of xi minus mu hat MLE whole square. And now we can show that if I take the expected value of this, then right hand side also I have to take the expected values of each xi, and xi's are IID. So, each will have the same mean. So, therefore, we can show that expected value of mu hat MLE is equal to mu, that is the true parameter. So, that way mu hat MLE is an unbiased estimator. Now, if I take the expected value of sigma hat square MLE, then I will get same way I can expand this and take the expected value, then I can show that this expected value is equal to n minus 1 divided by n times sigma square. So, this is not equal to sigma square, therefore, sigma hat square MLE is a biased estimator. So, mu hat MLE unbiased estimator and sigma hat square MLE is biased. So, that way n MLE may be biased or unbiased. Next, one important property, if a sufficient statistic Tx exists for theta, then theta hat MLE is a function of Tx. So, if we know that a sufficient statistic Tx is there, then theta hat MLE must be a function of Tx. This proof is also easy. Now, by factorization theorem, that likelihood function is product of g of theta Tx into Hx. This is the factorization theorem, one part that involves the statistic, and theta, other part simply function of x. Therefore, if we take the logarithm, log likelihood function will be log of this part g theta tx plus log of hx. Now, since del L del theta at theta hat MLE is equal to 0, we will get del theta of log of g theta tx plus log of hx at theta hat MLE must be equal to 0. And this part does not involve theta, therefore, we will simply get del theta of log of g theta tx at theta hat MLE must be equal to 0. Since theta hat MLE is the solution of this equation, therefore, theta hat MLE must be a function of sufficient statistic Tx. So, this property we established. If a sufficient statistic Tx exists for theta, then theta hat MLE is a function of Tx. Next property is, if an efficient estimator exists, the ML estimator is the efficient one. So, this is an important property because we always look for an efficient estimator, and if we know that it exists, then ML estimator will be the efficient estimator. Now, suppose an efficient estimator theta hat exists. We know that efficient estimator satisfy the Kumar bound with equality, and if we apply the Kumar theorem, then the condition for efficient estimator is that the partial derivative of the log likelihood function del L del theta must be product of I theta and theta hat minus theta, where theta hat is the efficient estimator. This is the condition we get from the Kumar theorem. And in that case, theta hat will be the MVUE, minimum variance unbiased estimator. Now, let us examine this case. Suppose one efficient estimator theta hat exists. Now, at theta is equal to theta hat MLE, del L del theta is equal to 0. So, it implies that this is a constant C into theta hat minus theta hat MLE must be equal to 0, and this implies that theta hat MLE is equal to theta hat. So, we have established that if an efficient estimator theta hat exists, then theta hat must be equal to theta hat MLE. So, this is an important property, but here also we presume that the efficient estimator theta hat exists. Next property is the invariance properties of MLE. It is a remarkable property of the MLE and not shared by other estimators. So, if theta hat MLE is the MLE of theta and h theta is a function, then h of theta hat MLE is the MLE of h theta. So, here we know, suppose theta hat MLE is the MLE of theta. Now, h theta is another function, and for this the maximum likelihood estimator will be h of theta hat MLE. So, that is the invariance. The under transformation, that maximum likelihood point is invariant. So, whatever theta hat MLE is there, at that point corresponding function h theta hat MLE will be the MLE for h theta. We prove the result when h theta is 1 to 1. This is a simple case. Suppose u is equal to h theta, then theta is equal to h inverse of u, because 1 to 1 it is invertible. Now, del f del h theta, that will be equal to del f del theta multiplied by del theta del h theta. Now, this quantity exists and this is a invertible function. So, we can find out this. At theta hat MLE, this quantity del f del theta will be equal to 0, and this is usually non-zero. Therefore, we will get del f x theta del h theta at theta hat MLE is equal to 0. So, this will imply that this maximum likelihood estimator for H theta will be at H theta hat MLE. So, H theta hat MLE is the MLE of H theta. We have proved the invariance property for the simple case when H theta is 1 to 1 and differentiable. However, the result is true also when H theta is many to 1. Invariance to transformation is a remarkable property not shared by any other estimators. Example, in our example of IIT Gaussian case, suppose sigma hat square MLE, that is the MLE for variance, is equal to 1 by n summation I going from 1 to n of xi minus mu hat MLE whole square. Therefore, what will be the sigma MLE? So, that is the MLE for standard deviation, that is sigma hat MLE will be given by square root of this MLE expression. Therefore, this will be the square root of 1 by n summation xi minus mu hat MLE whole square I going from 1 to n. So, this is the MLE for standard deviation. Once we know the MLE for variance, we can find out the MLE for standard deviation using the invariance property. We will consider another example. Suppose xi's are IID B1 theta. This is the symbol for Bernoulli random variable with success parameter theta. So, xi's are B1 theta random variables. Find the MLE for theta and hence the MLE for variance of x1. So, here xi's are IID Bernoulli. Now, P of x theta, x is the vector x1, x2 up to xn. So, P of x theta will be theta to the power, the number of success is summation xi I going from 1 to n, because xi takes value either 1 for success or 0 for failure. So, that way summation xi will be the number of success. So, theta to the power summation xi I going from 1 to n into 1 minus theta to the power n minus summation xi I going from 1 to n. This is the likelihood function. So, if we take the logarithm, then we will get the log likelihood function, and this will be given by summation xi I going from 1 to n times log of theta plus n minus summation xi I going from 1 to n times log of 1 minus theta. So, now we can take the partial derivative with respect to theta and make it equal to 0, and we will get theta hat MLE is equal to 1 by n into summation xi I going from 1 to n. So, this is the theta hat MLE for this parameter theta in the Bernoulli random variable. Now, variance of x1 is equal to theta into 1 minus theta, which is a function of theta. You can consider any variable x1, x2 or any xi because they are IID. Therefore, we can find out the MLE for variance of x1, that is variance hat of x1 MLE, that is equal to, we will substitute theta hat MLE. So, theta hat MLE into 1 minus theta hat MLE, where theta hat MLE is given by the likelihood estimator of theta given by this expression. So, that way we have seen the application of invariance property of maximum likelihood estimator, and this has many uses in signal processing. Now, we will discuss large sample properties of MLE. We saw that if an efficient estimator exists, the MLE is the efficient estimator. Another attractive feature of MLE is that its behavior becomes better and better with more number of samples. So, that we will establish now. The asymptotic properties of MLE holds under the regularity conditions like those applied in deriving Kramer-Rao theorem. We will not discuss about those regularity conditions, but these conditions are usually satisfied in practice. The MLE is asymptotically unbiased and efficient. This is a remarkable property. Thus, for large n, MLE is approximately efficient. Asymptotic property means as n tends to infinity. Therefore, when we have large n, MLE is approximately efficient. We will explain the asymptotic efficiency property. We have to show that for large n, del del theta of L x theta is equal to I theta into theta hat MLE minus theta. This is the one we want to show. If we can show this, then this theta hat MLE will be asymptotically efficient. Now, we will start with the MLE condition del L del theta at theta hat MLE is equal to 0. Therefore, 0 will be equal to del del theta of L x theta hat MLE. Now, this theta hat MLE we can write like this, theta plus theta hat MLE minus theta, where theta is the original value of the parameter. So, we write this theta hat MLE by this manipulation, theta plus theta hat MLE minus theta. Now, we can apply the mean value theorem to this expression. So, we can write this as del L del theta plus theta hat MLE minus theta into, because we are considering this function. So, derivative of this function will be del 2L del theta square at point x theta 1, where theta 1 lies between theta and theta hat MLE. So, this expression we get by applying the mean value theorem. So, this quantity del theta of L x theta hat MLE is same as del x del theta plus theta hat MLE minus theta into del 2L del theta square at point theta 1 for some theta 1 lying between theta and theta hat MLE. Now, since left hand side is 0, so we can write del L del theta is equal to minus, if we take it to the other side, minus del 2L del theta square into theta hat MLE minus theta. So, we got one expression like this. We have established that del L del theta is equal to minus del 2L del theta square times theta hat MLE minus theta. Now, under the IID assumption, because we are assuming that x's are IID, we can apply the weak law of large numbers to this quantity. Actually, this quantity can be expanded as the sum of individual log likelihood functions. So, that way it is a sum of some large number of log likelihood function. Therefore, we can apply the weak law of large number, which means that this quantity del 2L x del theta square at point theta 1 will converge in probability to the corresponding expected value of del 2L x theta del theta square, and which is equal to minus of I theta. Therefore, we can write del L del theta is equal to I theta into theta hat MLE minus theta. So, we have established that for large n, when n tends to infinity, del L del theta can be expressed as I theta into theta hat MLE minus theta, which means that theta hat MLE is the efficient estimator. And if I consider the Kramer bound, therefore, limit for the variance of theta hat MLE as n tends to infinity will be given by 1 by I theta, where I theta is the Fisher information statistic, and it is given by this expression E of del 2 L del theta square is equal to minus of I theta. Thus, theta hat MLE is asymptotically efficient. The same relation also explains asymptotic unbiasedness of theta hat MLE, because you see that when this condition is satisfied, in that situation theta hat MLE is the MVUE, minimum variance unbiased estimator. So, this condition implies that this theta hat MLE will be also asymptotically unbiased. So, we have established that theta hat MLE is asymptotically efficient and it is asymptotically unbiased. Last property, we shall consider the consistency of MLE. Recall that an estimator theta hat is consistent if theta hat converges in probability to theta. In other words, limit n tends to infinity of the probability that mod of theta hat minus theta is greater than equal to epsilon will be always equal to 0 for any epsilon greater than 0. So, this is the condition for convergence in probability. Therefore, with this definition we can check whether theta hat MLE is consistent. Further, if theta hat is an unbiased estimator, then the condition for consistency is this: limit of variance of theta hat n tends to infinity is equal to 0. If this happens, then theta hat will be a consistent estimator. Now, it can be shown that under the regularity conditions, theta hat MLE is consistent estimator. So, we can show that it satisfies this property: limit of probability of theta hat minus theta greater than equal to any epsilon as n tends to infinity will be equal to 0. But we will omit this proof, but what we claim is that theta hat MLE is a consistent estimator under some regularity conditions, but those regularity conditions are satisfied in practice. The desired properties of theta hat MLE under large sample conditions make MLE an attractive estimator for the signal processing communities, because as we have seen that if we consider general properties of theta hat MLE, then they are not very attractive, because we have to presume something. But here these large sample properties ensure that theta hat MLE is asymptotically efficient and it is a consistent estimator. So, these properties also can be extended to multiparameter cases. Let us give an example. In the example of IIT Gaussian samples, theta mu hat MLE is given by 1 by n summation xi I going from 1 to n. This is the MLE for mu. Now, we can show that E of mu hat MLE is equal to mu. It is a unbiased estimator, and variance of mu hat MLE is equal to sigma square by n. Using the IID property, we can establish this. Therefore, limit of variance of mu hat MLE will be equal to 0, which implies that mu hat MLE is a consistent estimator. So, we have shown that maximum likelihood estimator for mu is a consistent estimator. This is a general property. To summarize, MLE may be biased or unbiased. If a sufficient statistic Tx exists for theta, then theta hat MLE is a function of Tx. If an efficient estimator exists, then MLE estimator is the efficient estimator. Thus, if we can write that del theta of L is equal to I theta into theta hat minus theta, then this theta hat must be equal to theta hat MLE. Then we establish the large sample properties of MLE. MLE is asymptotically unbiased and efficient. Thus, for large number of samples, MLE satisfies the Kramer-Rao bound with equality. Thus, for large n, MLE is approximately efficient. Theta hat MLE is also a consistent estimator, that we did not prove, but this is also a general property of maximum likelihood estimator. The desired properties of theta hat MLE under large sample conditions make MLE an attractive estimator for signal processing communities. Many signal processing applications we use, for example, there are application of mean, variance, median, etc., where the MLE estimators are used. These properties of MLE can be extended to multi-parameter case. Thank you.